Start. All right, let's start with lectures on pseudo-randomness and on pseudo-random generators. And so this is first of 4 lectures. So let me just start by telling you what I want to do, and we'll see how much of it we'll do by tomorrow. And kind of goals will be the main goal, as Luca talked about quite a bit in his lectures, is to construct pseudo-random generators for interesting / important classes of test functions. So this is what we want to do, and Luca talked about why this problem is important, how it arises in different contexts, and also gave us some examples of these objects, right? So what I want to do is take this a step further and talk about 3 things. One is somewhat very specific, but it sort of connects to the pseudo-randomness part of this workshop, where you're talking about polynomials or finite fields and pseudo-randomness within polynomials and things like that. And that's what connects to here. And this will be PRGs for low degree polynomials. And the second topic, which will probably cover most of this, which will probably take up most of the 4 lectures, is a generic way to construct pseudo-random generators from certain other objects, which are conceivably a little easier to conceive and also sometimes construct. Okay? And this is about constructing pseudo-random generators with provable guarantees from lower bounds. And you can also think of this, it's also known popularly as hardness versus randomness. There is a very important moral message that this will send, that if you have hard functions, then you have pseudo-randomness, and the other direction is often much easier. Okay? And then there's the third part, which is again going back to an interesting special class of test functions, and that will be for space-bounded computations. So these are the 3 parts, and they might seem like very disjoint, but they all connect to each other. Okay? So for example, here, this will connect to pseudo-randomness of polynomials. In fact, many earlier works on this topic use things like Grover's uniformity, stuff like that. The analysis we'll see doesn't use it, but still kind of borrows a lot or is inspired from those ideas. And here, this will naturally lead us to extractors, which David has been talking about. And hopefully, once we finish this, we'll see how to construct a very important extractor, very good parameters. Okay, and this will tie up to David's lectures. Okay, and here, once again, extractors show up as applications. So we will use extractors to construct PRGs. Okay, so here we're using PRGs to construct extractors. This is kind of vice versa. And this also ties us to, I'll say a few words about applications to streaming algorithms. Okay, and kind of try to think, complete the circle. You can also use hardness versus randomness to construct PRGs for polynomials. Okay. So I'll say a few words about that. So this is kind of a fundamental tool which you can do, which you can use to construct extractors. Then extractors also arise in constructing PRGs for space-bounded computations, and you can also use them to construct PRGs for low-degree polynomials, albeit with slightly worse parameters. Okay, so this is kind of the outline of all 4 lectures, and we'll see how much of it we'll cover. Okay, so let me start by doing a brief recap of the definitions, most of which Luca covered, just so that we are all on the same page, and we'll be extending many of those. So let's start with that. Okay, so the first definition, which is that of pseudorandom generator. Or PRG. Okay. So what is a PRG? So PRG is a function which takes few bits of randomness, which we'll denote as 0, 1 to the r. R is the seed length of the generator, and outputs many bits of randomness. Okay? And these bits are not going to be truly uniform, but they will appear random to a class of test functions, right? Such that against a class of test functions. So I have a family of test functions which are trying to distinguish the output of this generator from truly uniform strings. Okay? Against a class of test functions, G is being designed against that. And we'll say 2 things. One, G has G epsilon fools F. Okay? We'll say the generator G epsilon fools the class of test functions if the following holds. If I pick any test function from my class, it cannot distinguish the output of the generator on a uniformly random seed from that of a uniform string with error better than epsilon, okay, with probability better than epsilon. If for every test function, the following holds. If I look at the probability that f evaluates to 1, okay, and that the output of, so we'll think of these test functions as being Boolean valued. It's pretty easy to generalize to other domains, but this suffices for most of our applications. So we'll say epsilon fools the class of functions if the probability that f evaluates to 1 under the output of the generator is close to the probability that f evaluates to 1 So I take a uniformly random seed, apply the generator, I look at the output of the function, and here I just take a fully uniform random string. So I want this difference to be less than epsilon. Okay. So we say G epsilon fools F if this condition holds. G has error epsilon, and we'll refer to this parameter R as the seed length of the generator. Okay. And in all of these constructions that we'll talk about, you want G to be efficiently computable. Okay? So given the seed, I want to be able to compute its output in time complexity, which is typically polynomial, in the output length. Okay, that's our goal. And in Luca's lectures, you already saw some examples of generators for certain kinds of test functions. Okay, just do a brief recap. So if f is the class of functions that only depend on k bits. Okay, so the input is of length n, but I'm only looking at functions which are only allowed to look at k out of the n bits. Okay. Or k variables. Then what does this correspond to? This corresponds to k-wise independent distributions or k-wise independent generators, as Luca discussed. Okay. And another thing that Luca covered, which will come up again, is if f is a class of parity functions. So now my test looks at the n bits, takes a subset of them, and then computes its parity. Okay, that's my test function. I want to see if the parity is unbiased or not. Okay, so these generators which fool these class of test functions are not other than epsilon bias spaces. Okay. So in this language, things like k-wise independent generators and epsilon bias spaces correspond to these classes of test functions. Okay. Any questions about this?
Yeah. What is the space that's referred to in this epsilon bias space?
Okay. So I'll define it in a second, but this is just tying up to Luca's definition. Okay. So what is epsilon bias space? It's basically, you can think of as a generator G, which fools test functions. Okay, which are parity functions.
So if you have a generator, the range of the generator induces a probability space. So sometimes we call it we talk about the generator, which is the function, and sometimes we talk about the space.
Right. Okay, that's a good point, and I think I'm going to make this mistake again. So let me iterate the clarification. So sometimes when we say epsilon bias space, or sometimes epsilon bias generator, basically space refers to the range of the generator. Okay, and generator means that it's a function that is generating this output. Okay. All right. So, and we also saw some applications of k-wise independence, or Luca showed you some applications of k-wise independence and small bias spaces to various objects and their connections to codes as well. Okay. So let's start with these epsilon bias spaces and see what else we can do or what else we can ask. Okay. So G is an epsilon bias generator. If for every f, I'll write it in words and then maybe be more explicit. That is a linear function from So I'm looking at all linear functions which take an n-bit string, which we'll view as an element of f2 to the n, and they output a bit. Okay. the condition that I had before holds. So, well, let's say f is a non-trivial linear function. Then what is this number? Probability that f of x equals 1 under a uniformly random string is exactly half. Right? It's going to be 1 with, the parity is going to be 1 with probability half and 0 with probability half. Right? So in a sense, fooling linear functions or getting it in epsilon bias generator amounts to outputting strings whose parities are unbiased. Okay? And Luca talked about constructions which can do this, okay, where the seed length was very nice. So it's outputting n bits, but you can satisfy this condition where the seed length is only log n plus log of 1 over epsilon. So the seed length is nearly optimal. You need at least log n bits, and you also need log 1 over epsilon bits to get error epsilon. Now, given this formulation of epsilon bias generator, it makes sense to ask a natural question which generalizes this. So here I'm looking at f, which is a linear function. What is slightly more general than linear functions? Quadratic. Okay, so what if f is a quadratic function now? And the question is, can you design a generator which is pretty good? Can you get a generator whose seed length is nearly as good as what you had for linear functions? Can you get a generator with seed length log of n plus log of 1 over epsilon? Okay. And here, quadratic function refers to quadratic over the finite field f2. So we are thinking of f as a function from f2 to the n to f2. Okay, from the finite field f2 to the n to f2. And here we can think of f2 as just being the set 0, 1. Okay. For example, you can take f of x, which is x1 times x2 plus x3 times x4 when n is even. Okay, this is an example of a quadratic function. Can we design generators which fool these kinds of test functions? Okay, so it's a natural generalization of what we did for linear functions. Okay. And more generally, you can ask, what can we do if we have a degree d polynomial? What if you have a cubic function? Okay. And that would be, for example, you can take things like x1 up to xd plus xd plus 1 up to x2d, and then all kinds of things. You can group things arbitrarily and so on. Okay. Can I still get the sort of guarantee that we had before? Can I get a generator with seed length which is as good as what we had before? Okay. And so what I'll do is hopefully give a construction which satisfies, which fools these degree d polynomials, has really good seed length, at least when d is a constant, like quadratic or cubic polynomials. And we'll see the analysis connects to some of the ideas or at least conceptual things that show up in works on pseudorandom polynomials or in works on arithmetic combinatorics over finite fields. Okay.
So
D-wise independent generator would be sufficient, right?
That's a very good question. So let's think of that. So let's do some candidates. Dy is independent. Okay. You can ask, what if my generator is outputting a sequence of bits where any d bits are kind of uniformly random. So it's a generator which fools all test functions which only look at d variables. Okay. Does that work for these kinds of things? Well, actually not. Okay. It even fails for degree 1. Okay. So you can show that there exist n minus 1 wise independent generators / spaces. Okay. Which are not, let's say, even 1/3 biased generators. Okay. Yeah.
So further, I want to point out that Luca actually showed an example.
Okay.
But this is a different example that you have in mind, so it's good that you show another one.
It might not be that different, but
the key point is that if the function were a polynomial over the reals, that would be exactly right. But this is a function over mod 2.
Mod 2. The parity can make things difficult. So let me just state this example, and this example will also illustrate this conceptual switch I'll do often. Okay, so as I said here, I'm going to talk about spaces versus generator. Okay, so sometimes it's more convenient to talk about generators, and sometimes about the spaces. Okay, so what do I mean? I'll just say it in words. So we're going to explicitly define the generator here, right? But we can also look at what distribution the generator induces on n-bit strings. Okay? So some generators are easier to describe by explicitly stating out what the distribution on n-bit strings is. Okay.
So just one quick clarification. When you mention only a generator that's epsilon biased, with not specifying against which class, so is it linear functions?
It's all linear functions. Okay. Yeah. So epsilon biased is kind of maybe not the, well, that's the terminology that came up. Epsilon biased spaces refers to test functions which fool linear tests. Okay.
In fact, linear mod 2.
Linear mod 2, yes. Linear mod 3 things are very different. Okay. I'll say maybe a word about that in some point. Okay, so here, for example, I'm going to describe a distribution on n-bit strings, which is n-wise independent. Okay, meaning this distribution, when I draw samples from it, it will fool any function which only depends on n minus 1 bits. But it's not even 1/3 biased. So what's the distribution? D is uniform on all. Can everybody see here? So I'm looking at the distribution which is uniform on all strings whose parity is 0. Okay, all strings which have an even number of ones. Right, and it's not too difficult to show that it is n minus 1 wise independent. Why? Because if I take out one bit, then whatever the remaining is, I can set that bit to be the parity of the n minus 1 bits, and I'll get a string whose parity is 0. So any n minus 1 bits of this distribution are actually uniform, have a uniform distribution. Okay? But does it fool linear functions? No, right? Because there is a linear function which is constant on this distribution. What is that linear function? This guy, right? So if I take a linear function, which is just the sum of the bits, the mod 2, then that function is constant on this distribution, but this fools all test functions which only look at n minus 1 bits. Okay, so that kind of rules out this example. Okay, so what else might you ask? What is another natural candidate? Well, you might be a very optimistic person and say, okay, I have a generator which we did in some detail, and we have a generator which fools linear functions. Okay, does that fool degree 2 functions? Well, it turns out that that doesn't work here. Next candidate is epsilon bias generators, or generators fooling linear tests. Okay, so n minus 1 bias independent didn't work. Does epsilon bias space work? Well, these at least we know they fool linear functions because that's where they're coming from. Okay, and unfortunately, even this doesn't work, and you can construct examples showing that this doesn't fool degree 2 test functions. Okay, so meaning there exists in
basically just take the pre-image of the 0 set of a full rank degree 2 polynomial?
Yes, exactly. So I won't go into this example in more detail, but as Daniel said, a counterexample is to kind of generalize this a little bit. Okay, I'm going to look at a distribution which is uniform on all strings x such that x1 times x2 plus x3 times x4 plus so on up to xn minus 1 times xn is 0. Okay, so this is a degree 2 polynomial. It's a very simple degree 2 polynomial where I look at parity of products of pairs of bits. Okay, and this is a distribution on n-bit strings, and it turns out, you can prove this with some Fourier analysis again, that this really has very good bias. It fools linear test functions with exponentially small error, 2 to the minus omega n. Okay, but does it fool degree 2 functions? No, right? Why? Well, here's a degree 2 function, degree 2 polynomial, on which is constant on this distribution. Right? So it's very bad for fooling degree 2 test functions. Okay? You can always, more generally, you can show that there are distributions which fool test functions of degree d minus 1 with nearly exponentially small error, but do not fool degree d test functions. Okay? All right.
Is it easy to describe the exponentially small set on which you get the bias?
Oh, this is basically uniform on this set. So this is my distribution D.
Okay.
So this set is uniform on all strings whose which satisfy this condition.
Okay.
x1 times x2 plus x3 times x4. Okay. So this is a set. This is a distribution, and I'm claiming that this distribution has exponentially small bias.
Yeah, I'm just asking why is it not 0 really, I guess.
If you have 0, that's a different story. If you have 0, then you're basically uniform. So you cannot get 0. But this requires some proof, which I'm not doing. It's not too difficult, but you do need to do some calculations. Okay? Any other questions about this? All right, so we have 2 approaches so far, and both of them have been shot. Well, what else can we do? As it turns out, this problem was actually first studied in a much more general context by Luby, who's here, and Velikovich and Wigderson in 1993. Okay? So they gave a generator which builds on this hardness versus randomness paradigm, the techniques that I'm going to talk about in lectures 2 and 3, and showed how to use that general construction and instantiate it in a very clever way with a well-chosen hard function to get generator with seed length that is much better than n, but not logarithmic. It's really exponential in square root of d times log n plus log 1 over epsilon. Okay. So, I mean, if you think of d as a constant, it's basically exponential in square root of log of n over epsilon. Okay, it's like 2 to the root of log n over epsilon. So, which is worse than what we had for linear functions, which was log of n over epsilon. Okay, and this stood for a long time until Bogdanov in 2005, I think, gave a construction for large fields. Okay, so I'm going to talk. I'm just going to state this in words. I'm not going to define what it means to be a PRG which fools degree D polynomials over large fields, but it's kind of the natural generalization where it replaces F2 with a field like Fp, or P which is bigger than the degree. Okay, for those kinds of fields where the field size is much bigger than the error and the degree, Bogdanov gave a construction. Okay, and then there was a flurry of activity. Bogdanov and Viola in 2007 gave a construction for GF2. Somehow F2 seems to be the hardest case of this problem. Okay, they gave a very nice construction, which is the one that we'll see. It introduced the idea of combining linear test functions, but their results were conditional. Okay, that work gave a construction and proved that it works if certain inverse Gowers norm conjectures held. Okay, so this work really drew this remarkable connection between fooling low degree polynomials and all this work that was happening in the context of arithmetic combinatorics using Gowers uniformity and things like that. And there were some very nice conjectures there, which are known as inverse Gowers norm conjectures, which basically wanted to say that if the Gowers norm is of certain value, then you get some correlation of polynomials and so on. If those conjectures were true, they show that their construction actually fools low degree polynomials. Okay? But unfortunately, these conjectures were actually shown to be false later on. But even before that happened, Lovett in 2008 kind of give a different proof of the same construction. Unconditional analysis of the same construction. And finally,
maybe just
yeah.
so they're not false in general, these conjectures. There's false
Oh, yeah.
characteristic.
Right. They're
I did say that earlier.
yeah, they're only false for GF2, which is what I'm focusing on. Yeah, over larger fields and so on, they could also get some unconditional results. And there are variants of these things which are known to be true, but I'm not sure if they can actually be used for this problem directly. Okay, but
So you're saying the construction is secure, but the initial thing was based on vacuous claim.
it's not exactly vacuous. I mean, there's a slight generalization of this conjecture which is known to be true. So conceivably, you could make it work with that thing, but still, you had like a direct analysis 2008. So we've been stuck. We've been following that.
And the seed length is d times log n plus log n.
I'll tell you what the parameters are in a second. Okay, and then Viola in 09 gave an even simpler, or let's say, give a very clean and simple analysis. Okay, and what I hope to do in the remaining 20 minutes is to talk about this analysis, what the construction is, which comes really from Bogdan and Viola. Okay, and how, I mean, I'm not going to dig deeper into how it relates to this stuff on Gower's norm and so on, but the ideas, maybe I can say a few words about. Then I'll say how this analysis of Viola works, which is actually very simple in hindsight. Okay? All right, so what Bogdanov and Viola suggested, their construction, was the following. So we know that tests that fool linear functions do not work for fooling even quadratics. Okay? So what else can we do? Well, they had this remarkable idea, which is XOR, independent copies. They said, a single epsilon bias space is not working, but what if I combine several of them? What if I take like 4 of them and combine them in some way? And the combination is also very simple. It's the XOR. Okay? So what is the generator now? So there is some parameter L, which will denote how many copies you are taking. And they said, well, let's define a generator. Okay? Which takes L seeds of length R each, which will use to generate, which will use as a seed for a generator fooling linear tests. That is, we'll use each one to generate a sample from the epsilon bias generator. Where G of y1, y2 to yl is the XOR. This is the output. So G1 here denotes, means that it's a generator which fools linear functions, degree 1 polynomials. Okay? So I take a generator which fools degree 1 polynomials, evaluate it on the first R bits, and take the same generator, apply it to the second R bits, and so on. Is there a question? Okay, so this is the generator now. Okay, so in a sense, I'm XORing or combining different samples or independent samples from the epsilon bias space. Okay, is this construction clear? And if you really want to get some intuition about it, I suggest playing around with this distribution. Okay, so just when you're at home, you can see what happens if I XOR 2 independent copies from this distribution. And you'll see that some nice cancellation happens, and it does in fact fool this polynomial if I XOR 2 independent copies. Okay. That's the candidate construction now. You're combining multiple copies. And how many copies do you need is a good question, and that will determine the seed length of your generator, right? If I take a few copies, then it's very good because I have nearly optimal seed length generators for fooling linear test functions. Okay? So I can use that as a black box, and my seed length will just get multiplied by how many copies. So Lovett in 2008 showed that taking L equals 2 to the D, where d is the degree of the polynomial that you're trying to fool. So for example, if I want to fool quadratics, then I need to XOR 4 independent copies of small bispaces, epsilon bispaces, or tests that fool linear functions, where G1 is a So if I take 2 to the D copies of generators which fool linear test functions with very good error, epsilon raised to the power 2 to the D, okay, then this function G fools, or epsilon fools, degree D polynomials. Okay. And Viola in 2009 improved this to just L equals D. And this remained the same. Okay? And everything else is the same. So if I just take 2 copies of epsilon bispaces and XOR them, I'll fool all quadratics. Okay? In hindsight, it's kind of a natural construction to try, and it does turn out that it works.
Do you have a low bounds at d log n plus log n?
That's actually a good question. So even in BV, Bogdan Viola, they showed that XORing D minus 1 copies not enough. So this counterexample again kind of goes back to here. Like you can give a construction which is kind of a generalization of this.
But I'm asking in general, so like for epsilon bispaces, we have a low bound, log n plus log 1 of epsilon for any construction.
Right. And that's also known. So there is a lower bound on R, which is d log n plus log 1 over epsilon.
Like parentheses, right? Log 1 of epsilon is also multiplied by d.
No.
Oh, so log 1 of epsilon is not interesting.
Yeah.
So here it's only suboptimal because you multiply log 1 of epsilon by d as well.
By 2 to the d, actually. I'll say that in a second. Okay. So the question was, is there a lower bound? And there is a lower bound on the minimum seed length you need to fool degree d polynomials. Yeah, which is d log n plus log 1 over epsilon.
What is your bias in this lower bound?
Here, epsilon.
No, the one above.
This one, it's like exponential. Like there are d minus 1 copies of exponentially small bias generators. Okay, when you XOR them, it does not fool degree d things, even with error like 1/10 or something. It's kind of a generalization of that sort of result. Okay. And what does this Viola's construction imply? If you instantiate it with the best known generator for linear functions, what do you get? I get a generator which works with seed length O of d times log n plus 2 to the d times log 1 over epsilon.
So you do lose something in the error term. So you do lose something in the error term.
Yes. And this 2 to the d is actually very important. I mean, you'll see where it comes up in the proof. And it's very important because it says that this is useless if d is log n base 2. Okay? And doing anything non-trivial for degree log n base 2 is a very important open problem because we don't have even correlation lower bounds and so on. Okay? So can I get even seed length which is little of m when d is log n base 2? Right? Even that's open. Whereas when d is slightly smaller, you get much better. Okay?
Are there natural functions which are expressible by degree like order of log n or like log square of n? I'm trying to see other like interesting Boolean functions such that if you write them as polynomials, it is kind of log or polylog or something like that.
There must be, I'm not sure.
Circuits can be approximated by polynomials as poly.
That's one reason why this log n is important.
Approximated over like reals or over like exactly, but over the fraction of the
over
domain?
reals or over F2 or...
Like Rasmussen-Smolensky type stuff. Yeah. Okay, so let me say a few words about the proof of Viola's construction. I'll state the two lemmas which go in there and then say a couple of words about how to prove them.
Very quickly, so if you pick like a random function with like with the seed lengths, is it known that like a random function will full degree D polynomials with high probability or something like that?
Yeah, it's known that if I take a random generator, this it matches this bound.
So this is tight.
That's right. Basically, it's like an enumeration over all possible degree D polynomials.
Okay.
All right. So the idea behind the proofs of in this proof and even in this proof is to use induction on the degree. Okay? So what they really show is that, or what Viola shows is, let's say I have a generator which fools degree, let me use D, it fools degree D polynomials. Okay? And let me use X or Y. I XOR with a generator which fools linear functions. So I'm XORing the output of a generator which fools degree D with one which fools degree 1, and he shows that this fools degree D plus 1. Okay. So this is the induction. There are some error parameters which show up, but basically if I full degree D and degree 1, if I XOR them, I full degree D plus 1, you iterate it, you get the theorem that I state there. Okay?
So I'm sure this was like the first thing they tried, but you know, what if you try like repeated squaring rather than doing by one, you like, you know, G1, G2, then G4, G8. So there are, I mean, does it, well, the construction is the same, but...
Yeah, it doesn't help. And also there's a lower bound here that D minus 1 copies are, D copies are needed. So if you're talking about the error,
Right.
okay, that's you might conceivably get some gains using that, but you'll see that the proof kind of fundamentally faces this 1 over 2 to the D loss, or 2 to the D loss. Okay? So the main insight behind the proof is this trick, or it's kind of unfair to call it even a trick, but it's a very nice observation of what happens to polynomials when you take their discrete derivative, directional derivatives. Okay? So let's say I'm trying to analyze this generator, and I'm going to denote, it's easier to work in the distributional space instead of generator space. Okay? So let's denote the distribution corresponding to evaluating this degree D generator on a uniformly random seed as W, and this as Z, just because I want two different letters. Okay? So this is the distribution on n-bit strings which fools degree D polynomials. This is a distribution on n-bit strings which fools linear functions, or it's an epsilon bias space. Okay? We're trying to understand what is it if I have a degree D plus 1 polynomial. Okay? And I want to study what is probability of f of is this close to the probability that f equals 1 on a uniformly random string. That's what we're trying to analyze. Okay? And so this is equivalent. This expression which I wrote down here, looking at the probability that equals 1, is equivalent to looking at this expectation. Okay? I'm looking at the expectation of minus 1 raised to the power f. If f is very likely to be 1, then this will be 1. If it's very unlikely to be 1, then this will be minus 1, and so on. Okay? If I can show that this is close to the expectation of f of u, where u is a uniformly random n-bit string, then I am done. Okay? So this is what we want to do. How do you show this? Well, Viola's analysis does a case analysis. Okay? So case 1, and then there is a case 2. So case 1 corresponds to polynomials where this is actually small. Okay? If you think of linear functions, one very nice thing there is that if f is a non-trivial linear function, then this is actually 0. The expectation of minus 1 whole to the parity is going to be 0 because it's 1 with probability half, 0 with probability half, they both cancel, you get 0. Okay? So the first thing he does is let's do a case analysis based on how big this bias term is. Okay? So expectation of f of u is small. It's big. The big case is somewhat easier to handle. So let me say what happens for the small case. So when the bias itself is very small, let's say it's smaller than epsilon or something, then it suffices to show that this expectation is also small. And I'm assuming this is very small. I want to say this is very close to it. So if I show that this is small, then I'm done. Okay? And here's the trick that kind of briefly showed up in Julia's talk in the morning, where I'm trying to do this expectation. Right? I want to bound this. Okay? So what I do is I apply Cauchy-Schwarz. Okay? I don't want to apply Cauchy-Schwarz to the whole thing because then I just get 1. If I square the inner thing, then I lose all the information that I have. But what you do is I apply Cauchy-Schwarz by first separating the variables w and z. Okay? So I'll show the proof in calculation and see why, say a few words about how you might think of this. Okay?
The square?
Okay, so right now I just applied triangle inequality, and now I'm going to apply Cauchy-Schwarz. Okay? So it will say that this is less than or equal to the square of the inner quantity. Okay? Sorry. And then there is a power half here because I'm doing Cauchy-Schwarz. Okay. So I have the square of this absolute value term here, right? And the trick is to replace this square with 2 copies of z. Okay, I'm taking the expectation of z and multiplying it with itself, right? This is equal to save some energy, I'm just going to rewrite it here, is less than or equal to minus 1 whole to the z prime. Okay. So I can replace the square of this term by it's the same as a product of two expectations. Okay. But now z and z prime are independent. Okay. And because it's minus 1 raised to this power, I once again get the XOR of these two things. Okay. So I'm looking at the expectation where z and z prime are independent and minus 1 raised to the f of w something something. Okay. All right. I can also remove the absolute values because I know it's a positive number, it's a square. And what will I do next? I'm going to change the order of the expectations. Okay? This power half is over the whole thing. Okay? So
You do use Jensen, right? Because the square root was inside, but you put it outside.
that was Cauchy-Schwarz. We don't. That was Jensen the first time, but after that you're not doing anything. Okay. So now the term inside that square root is equal to times expectation of w Okay. So I changed the order of the expectations. Why is this a big deal, right? And it's a big deal because of this fact that showed up in the morning's talk as well, that this polynomial now, if I fix z and z prime, I can think of this as a polynomial in the variables w. Okay? So originally f is a degree d polynomial. Okay? But if I look at this polynomial now, I can call this some polynomial h of w, which depends on what z and z prime are. Okay. But this polynomial turns out to have degree d. Okay. As degree 1 less than that of f. So XORing these two things allowed you to reduce the degree. Okay? And this is not just a magical thing, this is also the directional derivative of the polynomial. Okay? Basically, if I have a polynomial over g of 2, I look at its directional derivative, just like in the real case, the degree drops. And that's why you can use induction now. Okay? You did the simple calculations, and now you ended up with having to study polynomials whose degree was 1 less than what you started out with. But that was exactly what our distribution W was designed to fool. That was our assumption, our induction hypothesis, that you had these generators which fool polynomials of degree 1 less. Okay, so now you can carry your analysis forward. Okay?
Where did we use the small?
The degree is small?
No, like where did you?
Okay. So when you do this whole thing, I'm only showing an upper bound. Right? So if it's not small, it's not very good to show. You cannot get a good upper bound, and it's not going to be very good either. Right? So that's where the smallness comes in, indirectly. Okay. Any other questions about it? Yeah?
It's still not clear how you're getting rid of the z and z prime in the expectation.
No, I'm not going to get rid of it. There's some more calculations to do. But now you'll say, okay, I can replace W with a uniform distribution and then do some more manipulations to use the fact that z and z prime are actually fooling linear test functions. Okay? So I'm still cutting out maybe 3 or 4 equations and ending up here. But the main takeaway is that the main idea behind this construction analysis is that you can do these sorts of tricks by looking at directional derivatives to reduce the degree of the polynomial, and which allows you to use induction. Okay.
So this is a directional derivative. I mean, I can see directly the degree is less. I mean, is it helpful to think about derivatives? So
It's helpful in some contexts because, like, I mean, depending on where you come from, like, it might not be very natural to do this thing in the first place. Like, it's a few lines of calculations which are very easy to see and follow. But, like, why would you even do this, like, odd sort of Cauchy-Schwarz? You're replacing the squared with the product of two in the same things, and so on.
I guess I'm asking other like some useful lemmas, suppose as directional derivatives which could save some, which we can like remember a couple of times and then reuse them, because here I kind of see directly it's very cute, but it's
okay, so I guess this ties back to how the original works went through, like Bogdanov and Bogdanov-Viola. So where they looked at directional derivatives and they used that to connect to Gauss derivative, Gauss norm, and so on. Okay, so you can state this just by itself without directional derivatives, but I think there's no specific lemma which helps us here.
So it's not like you think like we should like remember some like on the side we put like Parseval inequality or something, that there is some things that we should remember about these discrete directional derivatives that could help in the future. It's just
one thing that you take discrete directional derivatives reduce the degree just as for normal things. That's the takeaway. Yeah?
Why is the degree one smaller?
Yeah, so that the easiest way to see it is to kind of expand it out. So if you take a monomial here, it's of high degree, and then expand this XOR out, the same thing in W appears here and here. The highest degree monomials of this polynomial, W XOR Z, do not depend on Z. They only involve W terms. But then the same things appear here, so when XOR them, they'll cancel out. That's why. Okay. Any other questions? If not, I'll stop here and then we'll resume in the next lecture. Yeah?
You have some introductory bibliography to post? Some
Yes. Yeah, I will. Yes. Maybe on the abstract or at the end of next lecture, I'll post something. Yeah.
So F3 instead of F2, how do you do this construction?
So basically, you look at characters. Right? You'll do characters. And then instead of looking at -1 whole to the something, you look at omega raised to that power, and things still work out in similar way. Nothing really changes in this analysis. Okay?
And the big case after?
The big case again is, well, it's much easier than this. In fact, what you can show is that if your bias is really big, then it cannot, even a generator which fools degree D polynomials will also fool degree D plus 1 polynomials whose bias is big. Like, you don't need the XOR operation when the bias is big. Yeah.
So I'm trying to think through in my mind how this missing step in the calculation goes. Is the point that we reduced a polynomial thing to a multilinear thing, and then we get, is that how we get to use our linear condition that
The degree becomes 1 less?
No, so I'm trying to think how we shoehorn the degree 1, the epsilon bias into this.
I see.
Is
So
it a multilinear function z and z prime, or is it something, yeah?
So once you replace W with U, okay, that's what you do, and then you do some Fourier analysis to reduce it to degree 1, okay? But that step just comes out very naturally, okay? All right? Okay, let's stop there.